So I think I will start. So Sytilidis, he hails from a little village called Castoria in Greece, and he did his undergrad at Harvard, and we did very well, and he got the David Mumford undergraduate prize, and then he went to Oxford in 2020, where he's doing his PhD under Chris Douglas. And I'm also now co-supervising him. And he's come to visit for 6 weeks, and we're going to chat about his project, and he's going to be giving this course while he's here. So thank you for giving the course, and great to have you here.
Thank you so much. Thank you, Bruce, for the introduction and for the chance to speak here. Just one thing, because I don't know, for the people who join online, can you hear well? I don't know if there is like any way you can interact via the chat. Let me know. Okay. Shamal says you can fine. Okay. If that ends up not being the case at some point throughout, please try to react in some way. And if not, we can start. Okay, so I want to minimize a little bit everything here so that it's easier to see. Perfect. So what I wanted to talk about is an introduction to pseudo-isotopy and to Morse theory. So I want to start fairly broadly and then specialize as we go on. But like the overarching question that I want to start with is, what tools do we have if we want to study questions about smooth manifolds? It's a very, very broad question. And there have been two very influential interplays in this story, one of which is directly relevant to what we'll be talking about. And the other I just want to mention because I think it's cool and it's good to have it at hand. So one interplay between the topology of smooth manifold is between the topology of smooth manifolds, differential topology, and maybe what we can call the algebraic topology of manifolds. So roughly, how this interplay goes is that one starts with a smooth manifold M, and then tries to construct some kind of space that captures some aspects of the topology of M. So ideally, that would be smoothness. Usually we can't do quite as well, but that's like very roughly what we are intending to. And then once we have the space that captures some kind of aspects of the topology of M, we compute some kind of algebraic invariant. So it could be homology, homotopic groups. And that's been like a very, very rich interplay that allows us to transport problems from differential topology to algebraic topology, and then use all the tools there to try and gain some information. And I should probably mention, usually when I say construct, that can mean many things, but two names that definitely need to be mentioned here is Podryagin and Tom. Usually these constructions go by some kind of variant of what's called Podryagin-Tom construction, but it doesn't matter for us too much. But definitely two very important names that will show up again and again.
Let me just take the opportunity to say that I will be emailing everyone his slides and also putting them up on our websites.
The other interplay, which we're really going to try and focus on quite a lot, is maybe something that I can vaguely say is an interplay between differential topology and dynamics on manifolds. So how that would go is we start again with a smooth manifold M, and now we choose some data. So at the very least, we choose the data of a smooth real valued function, or maybe a family of smooth real valued functions on M. And then the critical points of the things that we've chosen of these functions, and we study gradient flows and things relevant to that. And the punchline, the motto is that really the critical points, the number of critical points and the nature of the critical points of a smooth real valued function tells us something about the topology of the manifold that we began with. This is the punchline that we'll try to get to in this series of talks. And some relevant names that I should mention here. So the kind of functions that we choose typically would be Morse functions, or maybe variant Morse-Male functions, the kinds of families of functions that we choose. I'd be calling Cerf paths or like Cerf families, and we'll see what those things are in detail very, very soon. And the last thing that I wanted to say here, as there is a notion that's very central to differential topology that actually underlies both of these interplays, and it's very important. It's this notion of transversality. And we're going to spend next week talking about transversality quite a lot and with a lot of detail, but just wanted to put it out here. So it's like a very, very high level sort of schematic of some tools to address problems in differential topology and which corner of those we will be concentrating on. And one thing that I should say is that if one wants to appreciate any kind of interplay between two fields of mathematics, it's very useful. For me, it's very useful to have in mind a specific motivating problem that gets translated from one to the other, and you can now solve. We're not gonna talk about this in any detail, but just one motivating problem in this interplay that I'm a huge fan of, and it's actually the motivating problem that goes into Tom's work, is this Stignard's realization problem. So I'm just gonna mention it because I think it's pretty cool. So the problem asks the following: if you give me a topological space X and you give me a homology class, so it's like an nth homology class with Zemo2 coefficients. There are variants with like any coefficient systems, but if you give me that, there's the question of, can I find a smooth n-dimensional manifold M and a continuous map from M to X such that this map sends the fundamental class of M to alpha. So if you give me an n-dimensional manifold, its nth homology with Zemo2 coefficients, it's just going to be Zemo2. So there is a chosen homology class, which is the only non-trivial homology class, and that's the fundamental class. And so what Stignard's realization problem asks is, if you give me in any topological space, if you give me an nth homology class, can I realize it by a map from a smooth manifold? And that's a really cool problem, and it's actually one of the motivating problems that led Tom develop his theory on cobordism, which is really one of the landmarks of, and one of the very first key applications of this interplay between differential topology and algebraic topology of manifolds. We're not going to address this problem, but I just wanted to put it out there to as a motivating problem to have in mind if you want to study this interplay. So now I want to I want to present, like, similarly a motivating problem that shows up in this interplay between differential topology and dynamics. It's a problem in differential topology that we can try to connect to this theory of smooth real value functions and critical points, and try to get an answer through there. And this is the pseudo-isotopy problem. So it's another problem I'm a big fan of. So, but first, just we're going to go through the basic definitions. So the starting point is almost always going to be a smooth manifold, and for me, closed means compact and without boundary. And here I'm taking it to be n-1 dimensional. So we'll study the diffeomorphism group of M. So it's going to be the group of all diffeomorphisms of the manifold. I'm saying here, equipped with the Whitney's infinity topology. Don't worry about that. We're going to talk in detail about what that is next week. All you need to know is that there is some topology which you can endow this group with. So you have a notion of when two diffeomorphisms are near each other, and we'll discuss in detail what that is later on. But it won't matter for us now. Okay, so what's an isotopy? An isotopy of M is going to be a smooth path. So calling this capital F. So I is my interval, and I have this map from I to the diffeomorphism group of M. The terminology is going to be that, I guess, at time t, I want to think of it as a path, so sometimes we'll say at time t. At time t, the corresponding diffeomorphism will be f sub t. And the starting point, so when t is 0, the starting diffeomorphism is the identity. And well, I said a smooth path, so I have to justify what that means. If you give me capital F, so if you give me a path in the diffeomorphism group, that induces a map from the cylinder M cross I to M, and this is just a map that sends x comma t to f sub t of x, the value of the teeth diffeomorphism at x, and I want this map to be smooth. Okay, so that's what an isotopy is. And for everything we're doing, it's good for every definition to have a picture in mind. So the picture that I want to have in mind for isotopies is this den twist on the cylinder. So I can tell you, it's not entirely obvious what this picture represents, but what I want is my M, the manifold M, in this picture is the circle. So this direction is the direction of M. This direction is the direction of I. And at time t, I have a diffeomorphism that sends the red point here to the red point here. So that's how I'm just visualizing the isotopy. And so this here is an isotopy from the identity to the identity, because at time 1, I have, well, I'm just sending the point to itself. And I should also maybe write down, that's a mistake from the notes before, but I should also write down an example which is an isotopy from the identity to the rotation by pi, represented by a picture like this. And also, I want to say that if I am given an isotopy capital F, so I defined it as this map from the interval to the diffeomorphism group, well, I get a corresponding diffeomorphism from M cross I to M cross I. It's really the thing that I already wrote down. I'm just completing the extra coordinate by t. And again, the example to keep in mind with these pictures is the cylinder on the left gets mapped to the cylinder on the right and sends this red curve to this red curve. So hopefully that was more of a review, but any questions or concerns about isotopy as defined? Okay, so the next thing is that we want to talk about the collection of all isotopies on M. So this is going to be denoted by I of M. It's going to be a subgroup of the diffeomorphism group of M cross I that's induced by isotopies. So namely, H will be a diffeomorphism of M cross I that satisfies two properties. The first is that H of x comma 0 is x, and the second is that if I post-compose H by the projection to the I factor, well, that's the same thing as projecting to the I factor to begin with. That's the level-wise preserving condition. There is a left group action now. If you give me the group of isotopies, I can act on the group of diffeomorphisms. One thing that might be a little bit confusing notation-wise, you might be tempted to believe that, to think that I of M is a subgroup of diff M. That's not true. I of M is a subgroup of diff M plus M cross I, but it does act on the group of diffeomorphisms by just restricting to the top diffeomorphism of my isotopy. So restricting to the level 1. So namely, if H is an isotopy, the action of H on f of x is going to be, well, the value of H on f of x comma 1. That's what the action. I'm just looking at, in these pictures, I'm just looking at what is the top diffeomorphism that I get from my isotopy, and I compose with that. That's what the action is. And two diffeomorphisms are going to be called isotopic if they are in the same orbit under this action. And that's, yeah.
Can you scroll up a bit? I want to say something.
Yeah.
Definition of isotope.
Yes, let me know when to here. I don't see what. Oh, there is a bit of a lag, but
okay, it's fine.
but no, but where
No, it's fine. It's fine. I was just reminding this sort of defined this one. Then there's the induced.
Yeah. Yeah, I might be using those all interchangeably sometimes. Yeah, there's the isotopy, which is defined by this path, and then there is an induced diffeomorphism of that isotopy. I might sometimes, yeah, yeah. That I'll try to be careful, but I most likely will not always be. But yeah. Okay.
Because I'm asking that because like this subgroup of isotopes that we are talking, which is the subgroup of diffeomorphism of M cross I.
Yeah.
Actually the maps, the diffeomorphism that are induced by isotope. Okay.
Yeah, exactly. So the right thing to say is that this is the subgroup of diffeomorphism. Yeah, I think I write it, but I didn't say it, which is induced by isotopes. Exactly. Yeah, exactly. But I'm just going to be calling it the isotopic group of yeah.
Sorry, the action of what at the bottom sentence?
Where
The very last sentence, the definition at the bottom.
the
Two different organisms are called isotopic if they're in the same orbital reaction of.
oh, sorry. That's what happens when you change notation, and you don't update the entire document, which is something that will most definitely happen many times. Yeah, but I mean, yeah, exactly. The action just defined. I used to call this H for some reason, but I think I of M is a better name. Okay, is everything?
Just one question I have there. This definition of two diffeomorphisms being isotopic, if they're in the same orbit and the action of I of M, like you made it seem as if I needed this concept of extending isotopies to a diffeomorphism of the cylinder and stuff, but I could have stated this before. Once you gave the definition of an isotopy, I could have stated this definition, right?
Yeah, I'm actually, yeah, there's this is a bit of an overkill. The reason why I'm doing it this way is because I want to make very clear the passage to pseudo-isotopes.
Yes.
But it's definitely not
I see.
If I only want to talk about isotopies, that wouldn't be the way I would choose to say it. Yeah, exactly. And I don't know, maybe just following up on that, this remark is that, like, if we unpack the definition, then F is isotopic to G if there exists a level preserving capital H, so namely an isotopy, such that when we restrict to M cross 0, it gives us F, and when we restrict to M cross I, it gives us G. I should have done that in orange. I spent a lot of time color coding, but I wrote that in pink now. It's okay. But that's maybe a more familiar way of like how I would write it down. But if you unpack the definitions, it says exactly the same thing. Okay, so is everybody happy with isotopies? Okay, now we go to pseudo-isotopies. I'm basically going to copy paste everything that I did, but relax one condition, the level-wise preserving condition. So, so for the definition of pseudo-isotopies, we just relax the level preserving condition. So this is just going to be a diffeomorphism from M cross I to M cross I. I'm not requesting it to preserve levels. The only thing that I'm going to request it to do is, again, when at time 0, I want to be the identity. So this is pseudo-isotopy, is just going to be a diffeomorphism from M cross I to M cross I. That is the identity when restricted to M cross 0. And again, an example to keep in mind is would be something like that, would be a diffeomorphism that from the cylinder to the cylinder that sends this red line to, I guess, this red line. And so this is no longer going to be level-wise preserving. We have a level here where we have like 3 points, for example. And then I'm doing exactly the same thing. So we can define a subgroup of pseudo-isotopies. This is a subgroup of the diffeomorphism group of M cross I. Again, we have the same left group action from the group of pseudo-isotopies to the diffeomorphism group, which is given by, again, restricting to the top diffeomorphism that is defined by the pseudo-isotopy. And again, we have a definition of what it means for two diffeomorphisms to be called pseudo-isotopic, which is that they are in the same orbit under this action. So yeah, it's going through everything that we do with isotopies, but relaxing level-wise preserving condition. And well, one first observation is just by definition. I mean, we started with a notion and then we relaxed one of the conditions that define this notion. So in particular, that means that every isotopy, and I guess the same mistake here with H, every isotopy is a pseudo-isotopy, which implies that if two diffeomorphisms then they must be pseudo-isotopic. Okay. Is that clear? Now, the pseudo-isotopic question is basically, when does the inverse hold? So we got a more like relaxed notion of something, and it's a question of when are we actually getting something different? So under which conditions can we also conclude that two diffeomorphisms being pseudo-isotopic would imply that they are isotopic? And it would be if and only if in those cases. So that's the question.
Let me just ask, so P of M is, you say be the subgroup of pseudo-isotopies, but you don't quite define it. I mean, what is it defined, unless I missed it there? You say let P of M be the subgroup. Oh, is it above?
I mean, I defined what a pseudo-isotopy is.
Let me just go back to it. I think I was sleeping. There it is. Thank you.
Yeah. Right.
Thank you.
Oh, okay. So that okay. So it's take an isotopy, but it's not going to be level-wise preserving anymore.
It's just any diffeomorphism that at zero
is the identity. Yeah, that's the only thing I'm asking for. Exactly. Yeah. Exactly. Maybe I should have said we can also just like we could more directly define when two diffeomorphisms are isotopic. We can also more directly define when two diffeomorphisms are pseudo-isotopic. Again, it's exactly the same definition. It's just that this capital H is not required to be level-wise preserving anymore, just any diffeomorphism from M-side dimension. That's everything that happens. And again, I always want to have a picture in mind, and the pictures that I have shown you so far is like this picture representing a pseudo-isotopy and this picture representing an isotopy. And all I wanted to note is that if you look at this red curve, there is an isotopy of the cylinder that sends this red curve to this red curve. So, if I have two diffeomorphisms that are pseudo-isotopic because of a pseudo-isotopy that's represented by the left-hand side picture, then I know that those two diffeomorphisms must be isotopic through an isotopy that's represented by this right-hand side picture. So it's like all I'm trying to say is that there are definitely cases when two diffeomorphisms being pseudo-isotopic would imply that they are isotopic. So it's a reasonable question to ask. And well, that's the question we'll be asking. So there's basically two things to do for today. One is to persuade you that this is an interesting question. And then the other is to persuade you that there is a link between this question and what I've been writing down in the beginning, this interplay of differential topology and dynamics on manifold story. So I'm going to start with just telling you basically what's known, or I guess what Cerf proved about this question and what some implications of it are. And then I'll tell you what the connections are with, I guess, Morse theory and all of this stuff. So are we on board and happy going? Okay. Let me get a bit of water. Right. So what Cerf proved is the following. So Cerf proved that if you give me a smooth, compact, and boundaryless manifold that's also simply connected, and its dimension greater than or equal to 5, then the group then the group of pseudo-isotopies is connected. That's what he proved. The first thing that I have to tell you is why that implies why that is a positive answer to the pseudo-isotopic question under those assumptions. So, so the first thing that we'll prove, we're not going to prove this today. It's going to be our goal to try and sketch a proof of this by the end of the course, but it's gonna take a while. But we can prove how this implies a positive answer to the pseudo-isotopic question. So so the first corollary is that under these assumptions, so smooth, closed, simply connected manifold of dimension greater than or equal to 5, any two diffeomorphisms of M are going to be pseudo-isotopic if and only if they're isotopic. So, okay, how do we prove that given the theorem? Well, what does the theorem imply? The theorem implies that if you give me any pseudo-isotopy, so a pseudo-isotopy, again, it's a diffeomorphism from M cross I to M cross I, there will exist a path, so I'm calling this capital gamma. There will exist a path in the space of pseudo-isotopies. The path will start at the pseudo-isotopy F, and it's going to end in the identity, right? Well, I know that if I know that the space of pseudo-isotopies is connected, it means that any two pseudo-isotopies are connected by a path, and the identities are perfectly reasonable, in fact, the most reasonable pseudo-isotopy one can ask for. So I have such a path. Okay, now.
Sorry?
Yeah.
Previous you mentioned that the isotope is inside pseudo-isotope. So I don't understand the if and only, like, can you explain to me why?
Right, yeah.
You
So,
say that?
Mhm.
Because I feel like it's trivial.
Right. So one way is indeed trivial. Right. So indeed it is true that if two diffeomorphisms are isotopic, then they are pseudo-isotopy. So isotopy always implies pseudo-isotopy.
Okay.
That's always true because it's a weaker or stronger notion. I always get my English wrong for that. But you know, stronger notion. Exactly. But the other way around. So from pseudo-isotopy implies isotopy. That is highly non-trivial.
Okay.
Is that clear? And but what we're proving, I guess, well, what Cerf proved is that, yeah, if your manifold is simply connected of dimension greater than or equal to 5, those two notions are actually equivalent. So and that's what we want to prove. So yeah, so now if we are in this situation and you hand me in two diffeomorphisms that are pseudo-isotopic, well, what do I know? I know by definition that there exists a pseudo-isotopy. So that's this capital F. And F and G are related by the simple formula. So F of X is going to be the value of the pseudo-isotopy at the pair G of X, 1. That's how we defined the what it means for two diffeomorphisms to be pseudo-isotopic. Okay, I don't have too many things in my disposal, so but gladly what I have is enough. So what I want to prove to you is that these two diffeomorphisms are actually isotopic. So I need to construct a path from so I need to construct a path in the space of diffeomorphisms. Okay. What am I going to take? Maybe putting yellow was not the smartest because I also can't see. No, it's fine. I think I can remember. So we're going to take at time t, I need to produce a diffeomorphism to you, So I need to tell you where this diffeomorphism is going to send, I don't know, X. I guess, well, we have something to play with. We have this path gamma, capital gamma, in the space of pseudo-isotopies. So I'm just going to put gamma of t, and I'm going to evaluate at g of x, comma 1. So this here is an element of M. This here is an element of M. This is a diffeomorphism. And what's happening at t equals 0? Well, at t equals 0, capital gamma of 0 is just capital F. And capital F of g of x, comma 1 is just f of x, right? So at time 0, little gamma of 0 is f. And then at time 1, capital gamma of 1 is the identity. And, well, that's just going to be g. So I constructed a path in the diffeomorphism group that starts from f and ends in g. So I proved, using Cerf's theorem, that the pseudo-isotopy group is connected. I can prove that pseudo-isotopy actually implies isotopy. You seem concerned.
Yeah, I think I'm maybe being a little bit slow.
No.
We need this to be level preserving, right? Isotopy, not just the pseudo-isotopy.
Well, so that goes back to this. I have three different things that I'm calling isotopies here, but that was the original definition, right? The original definition was just the path to the diffeomorphism group, which then induces a level-wise preserving diffeomorphism of M cross I. Yeah, is that everyone? Yeah.
I'm still looking on the wheel, like from this assumption like suppose F and G and T apps so by that exist and capital F which such like this one. Which condition is that, like from the definition of pseudo-isotopy?
That's well, that is the. So let me go back to the definition of pseudo-isotopy, but that's basically the. Well, yeah. See, I didn't spell out the definition of pseudo-isotopy, but yeah. So maybe I can say.
That picture that you had, the one picture you could just label the bottom by F, like that picture there. If you just the bottom you have an F and the top you have a G kind of thing.
Yeah.
It makes sense. Or actually it's the other way around, right? It's G on the bottom and then F on the top.
Yeah.
Okay.
I mean the way I want to think about it is, let me see if I can think of a good picture to draw. But well, I defined for you an action of the group of pseudo-isotopies on the group of diffeomorphisms, right? And how did that action work? Is if you give me a pseudo-isotopy, that's a diffeomorphism from M cross I to M cross I. If I just look at the top level, that gives me a diffeomorphism from M cross 1 to M cross 1, which in particular is a diffeomorphism from M to M. And I'm saying that F is pseudo-isotopic to G if there exists a pseudo-isotopy such that if I precompose G with the top level diffeomorphism that this pseudo-isotopy defines, I get F. Right, because that's what the action is. The action on the space of diffeomorphism is just a precomposition with postcomposition with the the top level diffeomorphism of the pseudo-isotopy. And the top level is just what I get by putting this one here. That's what this one does. It just tells me to, like, capital F is my pseudo-isotopy, capital F bar comma 1 is the diffeomorphism of the top level, and that's post composition of G with that. Is that clear? Yeah. Okay, how's everyone feeling? Is everyone convinced that if the pseudo-isotopy group is connected, then pseudo-isotopy is equivalent to isotopy? That's what I want everyone to be convinced about.
Yeah, but still have one problem in the theorem, like, because why did we use that? Because what you expect is like use the condition that the pseudo-isotopy group is connected, right?
Yeah.
I mean, that's the path down.
Yeah. So that's what allows us. That's exactly, yeah.
Okay.
That's why this capital gamma exists. Yeah. I get
The way
a.
I think about it, is from a pseudo-isotopy, by restricting it to the top level, you actually get a diffeomorphism of the manifold.
Yes.
And so if you've got a path in the space of pseudo-isotopies, then restricting each of those to their top level can give you a path of diffeomorphism.
That's exactly
But you does, because that gamma to exist means it's path connected, not connected, or is it the same thing?
Sorry.
Did I like? Because
Oh yeah,
the sense of gamma, it implies a simply connected.
well, I'm yeah, connected does imply path connected for me in this case. I didn't. I mean, I'm not going into
It's
actual details of the topology of the pseudo-isotopic group, but it's nice enough where this is I never work with anything that's where this implication that I refuse to consider cases where this just doesn't. But it is true. I could just say path connected there instead of connected. We have a slight issue, which of course we're going to have, but let me try. Oh, it's because my iPad just got disconnected from internet, but hopefully we'll resolve this soon. Are there any questions, comments, concerns in the meantime? No. Okay. Join without video. Does anyone have a nice math joke that you'd like to share? No audio.
So, yeah, like, I was going to. It's like it's like a diffeomorphism. Okay, that's fine.
No, please.
It's a tortured example, but okay. So the diffeomorphism of the circle is sort of, just think of some way I can move the circle. Someone's got a different diffeomorphism. He's moving the circle a little bit differently. And then an isotopy from one to the other would be sort of some way of moving the circles up and so that you can match the one diffeomorphism to the other. But in a pseudo-isotopy, you're allowed to take that circle and sort of wrap it all around. It's just as long as at the bottom and at the top, you line it up as a circle again. So you, in principle, have got more freedom to sort of twist it around. And so that's how it's a weaker condition for two diffeomorphisms to be pseudo-isotopic than to be isotopic.
Okay. So hopefully we're all fairly happy with that. The next core is, I mean, okay, you may ask, why would I care whether like pseudo-isotopy is equivalent to isotopy or not? I think Shimal has a question, or yeah, okay. Is the problem of going from a pseudo-isotopy to an isotopy somewhat related to canceling out critical? Yes, the picture Filippos had of taking a pseudo instead of someone. Yeah, exactly. No, this is very, very related. And in fact, that's exactly going to be the connection between this pseudo-isotopy problem to the theory of Morse functions and Cerf paths. That's basically this observation is quite key in this whole story, and we're going to make this observation hopefully very, very soon. But yeah, definitely very related. Okay, so yeah, so I just wanted to give an application. There are like more applications, but maybe one that's that I quite like, and it's fairly easy to, I think, see, which is the pseudo-isotopy theorem of Cerf implies that in dimensions greater than or equal to 6, if I look at the diffeomorphism group of the n disk, it's going to be connected. So let's try to prove that. It's quite fun. Unfortunately, I wrote this without drawing pictures. That's partially because I don't have great pictures that I can draw here, but definitely this picture is not in dimensions greater than or equal to 6. But anyway, so if you give me 2 disks and you give me a diffeomorphism between them, I want to do basically 2 things. The first thing, which I'm just going to say, and hopefully you're all going to be convinced, is that if this is like the disk of radius 1, I can maybe look inside it to a smaller disk of radius 0.5. And there's going to be an isotopy that's going to take my diffeomorphism and it's going to turn it into a diffeomorphism that actually is the identity on the smaller disk. I can always do that. So I can make any diffeomorphism of the disk. I'm not making any requirements for this diffeomorphism to be pointwise preserving at the boundary, just the diffeomorphism of the disk. I can turn with an isotopy to a diffeomorphism that fixes a small neighborhood of the origin.
That's an interesting little thing, right? Because it's sort of, is it sort of a consequence of the Brouwer's fixed point theorem kind of thing? Or is it slightly easier than that? Because like, if Brouwer's fixed point theorem says that there is a fixed point of, sorry, I think it's that's for a general map, not necessarily diffeomorphism. I think for diffeomorphism it's easier.
Yeah, I don't think. Yeah, I don't think.
Okay.
Yeah.
Okay. Sorry.
Yeah. And now, okay, so now I have a diffeomorphism, or I'm isotopic to a diffeomorphism that is the identity on the brown part. And I can look at, well, if it's the identity of the brown part and it's a diffeomorphism, it's definitely going to send the orange part to the orange part, right? So it's going to be a diffeomorphism from the complement of the disk of radius 1.5 and the disk of radius 1 to itself. Well, that's exactly a pseudo-isotopy, right? So what is the orange thing? The orange thing is S of like S is the n-1 sphere across an interval. That's what the orange thing is. And a diffeomorphism which is restricted to be the identity on the n-1 sphere across 0, that's exactly a pseudo-isotopy. So the pseudo-isotopy theorem would then imply that this pseudo-isotopy is isotopic to an isotopy. And so now my original D, there is one more thing. So the pseudo-isotopy theorem implies that the pseudo-isotopy is isotopic to an isotopy. That also implies that it's going to be isotopic to the identity. So I'm using here something which I was going to say a bit later without realizing that I need it here. Or wait a minute, do I actually need it here?
It's starting on the identity by definition on the boundary of that dark brown ball. So it's clearly from the start identity.
No, it's starting at the identity. I'm not saying.
Australia, this is just the connectedness of the pseudo-isotopy.
Yeah. Exactly. Sorry, I'm not. I don't need anything more. Yeah. Exactly. I don't need anything more. Exactly. So right. So I know that the pseudo-isotopy that's defined in this orange part is itself going to be isotopic to the identity. And I know that my original thing was isotopic to the identity on the brown part. So it must be, D must be isotopic to the identity, and therefore this space is connected. How does everyone feel? Is everyone happy with? And I mean, diffeomorphism groups of disks are very, very interesting. And I mean, here, I just want to say maybe a couple of words here, because one of the reasons that makes this fairly approachable is that we are talking about diffeomorphisms without any restrictions. So if one were to consider a similar group, like the diffeomorphism group of the disk rel boundary, where I'm restricting to those diffeomorphisms that fix the boundary point-wise, that's a much more complicated group. And like its pi is 0, I don't think it's known for like any value of n greater than 3, I think. So there is a lot of work that people have done for higher homotopy groups and other algebraic invariants for this group here. And maybe just as a fun remark, I haven't seen this before, but this would imply that all disk bundles over S1 are trivial for n greater than or equal to 6. So if you have seen this before, and if this says something to you, it's like if you look at the classifying space of the diffeomorphism group, pi 1 of it classifies basically dn bundles over S1, because this is the space of maps up to homotopy from S1 to the classifying space, and that's the same thing as pi 0 of the diffeomorphism group dn. So, which has shown that it's trivial. This is I put that in gray because if you remember, gray was the color coding for this interplay between differential topology and algebraic topology of manifolds. That's probably the only example we'll see of that, but it's a very classifying space of diffeomorphism groups are really a part of this interplay. That's quite important. Yeah, so hopefully everyone's very excited now about the pseudo-isotopy theorem, and it's very motivated and wants to learn about its proof. And but before I'm going to this section, I promised a break, and now it's a good time for a break. So yeah, so I suggest that we take a 10-minute break, and then we resume with the next section, which is about relating this problem to smooth real value functions at critical points, basically like Shimal suggested. So let's take a break now. And
the result just above there.
Sorry?
The result just above there.
Which result?
On that one?
Yeah.
So, that should really say SN. Okay, SN.
No, it's S1. Yeah.
S1. Okay, so this bundles of dimension n.
Yeah, and yeah, that's right. So and disk. Yeah.
Okay.
Yeah.
It's great. That's the point, right? Yeah.
Please do.
Okay, thanks for the process. Great. Speak to them again. You get this, the final thing about the disk bundles? You happy with that?
Okay, we're going to start again. Other people online, can you? Okay, you're on it first.
No,
Okay.
I'm just on it, but yeah, let's just see. They might have gone away on their own break now. But okay,
Yeah, we have.
you've received some applause.
Amazing. That's always good when it happens. Yeah. Always keen for that.
Okay, that's nice.
Okay, I just wanna take this window down so that you here don't need to look at me both ways.
Go for it, you can start. Yeah.
I'll start. Okay, so for the second half, hopefully everybody is super hyped about the pseudo-isotopy problem, and we're gonna see how it's related to critical points of smooth functions. And yeah, what does it have anything to do with what I promised? And the first thing is basically, I'm just saying that we already got a little bit of a glimpse of that. It's exactly the remark that Shimal made. So the pictures that I drew, I tried to draw them suggestively to like hint that there is some connection. So here, like if we take in those pictures the projection map, okay, no, the projection map, well, yeah, the height map of the cylinder. Here we are in this red curve, we have no critical points. In this red curve, we have two critical points. And I told you that this represents really a pseudo-isotopy. This represents an isotopy. The two of them, the fact there is an isotopy that goes from the left to the right, sort of the statement that we can cancel those two critical points together. That's just at a very high level, a bit of a hint of where that connection might come from. And we're now going to make it very, very, very precise. So, well, first I have to tell you what a critical point is. So if you give me a smooth real valued function, a critical point is going to be a point whose differential, the differential of the function at that point is 0. And well, basically that means that you can choose a coordinate chart. So there exists some coordinate chart. And well, if there exists one, that would be true for any, where I can calculate all the partial derivatives in this coordinate chart very explicitly, and I get 0 at the point corresponding to P for all of them. So that's what a critical point is. Now, I want to look at, I want to define some things that we are going to be using in order to make this translation from the pseudo-isotopic problem to a problem about smooth functions and critical points. And the first thing that I want to define is the space of all smooth real valued functions. So if I have a manifold M, I want to consider capital F, or I guess curly capital F, whatever, of M. That's going to be the space of smooth functions from M cross I to I. Again, it's a bit of a keeping track of the terminology. Most of the time when I have M, it's actually M cross I that shows up, but I'll try to point out when that becomes confusing. And I just wanna look at all the smooth functions that have no critical points on the boundary. So if I restrict to M cross 0 and I restrict to M cross 1, I won't be there. That's the space of smooth functions that I want to consider. Inside of it, and again, I'm saying it's endowed with the Whitney's infinite topology. We'll talk about the Whitney topologies next time. This isn't just a set. There is a natural topology that I can put in there. That's all you need to remember. And there is a kind of special subset of it and subspace of it, which is the space of those functions with no critical points, like anywhere. That I'm calling epsilon of M. And I would like to to make a remark. So, okay, so this space f of m, it's a huge space, and it's also a contractible space. I'm not going to prove that it's contractible, but the reason why it's contractible is because it's convex, really. So if you give me any two smooth real-valued functions, any linear combination of them is going to be a smooth real-valued function. So the space itself is convex, and any convex space is contractible. The proof is a little bit more complicated than that because I have to tell you what kind of space f of m is to use this, but that's basically the heart of it. So it's a contractible space. What that means is, I guess we talked about pi 0 and pi 1. I'm going to make a more general statement, but what it means is that if I want to calculate, say, the ith homotopy group, you can put I equals 1 or I equals 0 here, because that's all we're going to be using anyway. But if you want to calculate, say, the ith homotopy group of this space, epsilon of m, with base point pi 2. Now, I realized as I was writing this is going to be very confusing because the pi 2 here, what I'm calling pi 2 here, I'm calling the projection to the second factor from n cross I to I. Okay, so that's a little unfortunate, but this projection, I mean, if I'm telling you to consider maps from m cross I to I, this is like one of the most beautiful maps you can write down, and it has no critical points. So it is an element of epsilon of m, and it's one that we would like to consider. So, right, so I wanna, for some reason, maybe, and I'll tell you the reason in a bit, but for some reason, maybe I want to calculate the ith homotopy groups of epsilon of m, using the fact that f of m is contractible. Actually, that would be the same thing as calculating the I plus 1 homotopy group of the pair f of m comma epsilon of m, again with base point pi 2.
Can you just say a sentence or two about
Yeah.
what homotopy groups of pairs are?
Yeah, so I can maybe tell you, let's think of pi 1 of this pair. So if I just asked you to calculate pi 1 of epsilon of m centered at pi 2, you would have to look at like all loops that are based at pi 2. Here, what you want to do is you wanna look at that again, but now relative to epsilon of m. So a loop is now going to be trivial if it's homotopic to a loop that can live entirely inside epsilon of m. Right. So previously, if I just look at pi 1 of f of m, a loop there would be trivial if it's contractible, if it can be homotoped to a point. Now, I'm having a much more relaxed condition, which is a loop there would be contractible if it can be homotopic to something that lives entirely inside.
So it's like pushing down.
Yeah, yeah, I'm a little reluctant to say that because it's not, there's no formal way in which of one homotopy group by the other. But
it's so much reminiscent of quotienting a ring.
yeah, there is definitely a quotienting that comes. So yeah, yeah, I think it's an okay analogy to have. I don't know if it's a.
They're in the exact sequence.
There is, yeah. So and that's basically, maybe I should say, because I am using the long exact. So there is basically, if you give me a pair a comma b, I have I have a long exact sequence of homotopic groups that, let's see, I think it's pi1 of B in pi1 of A in pi1 of, if pi I of A relative B, and then it loops down to pi I minus 1 of B and carries on like that. I think that's what it is. So you have an exactness condition, so yeah, so that's basically how this group, the relative homotopic group, is related to the other homotopic groups. I think, yeah. And that's the exact sequence that I'm using here, really, in order to conclude, to make the conclusion that this remark is right. Because what I'm saying is that if f of m is contractible, like f of m corresponds to A in what I wrote down here. So if A is contractible, right? So that means that this guy here is 0, and here I'm going to I minus 1 of A again, and so this guy here is also 0, and therefore I have this kind of isomorphism. That's the isomorphism that I wrote down here. Okay. Does that help? Or basically what I wanna do, and again, you can put I equals 0 here in your mind, because that's really all we're going to be using. But if for some reason, and I'm going to give you the reason in a bit, but if for some reason you want to calculate homotopic groups of this space epsilon of m, one way you can go on about it is trying to calculate homotopic groups of this pair f of m comma epsilon of m. And if you want to do that, what this amounts to doing is thinking about families of smooth functions, right? So if say I equals 0, that would be a path. What is a relative loop here? It's a path of smooth functions that starts and ends in pi2, starts and ends in this path, in this function, which is given by projection to I. And then there is the question of when can such a path be deformed into a path of smooth functions that lies entirely within epsilon of m, which means when can it be deformed to a path of smooth functions with no critical points. This is the sort of, if you want to try and calculate this homotopic group, this is the sort of questions that you run into. And this is precisely what Cerf theory is about, trying to understand like families of smooth functions and when one can be deformed to the other. And that's really what this is about. And I just want to give you a little bit of the reason as to why you may want to calculate homotopic groups of this space and how it might relate to pseudo-isotopy. So I guess we just maybe of a fiber bundle here in the whiteboard. I wanna write down something a little bit more general than a fiber bundle. So basically, the big picture is the following. The big picture is that I can write down something which is a fibration. So it's a map from the pseudo-isotopic group of M to this space that I just defined, epsilon of M. It's a map that takes a pseudo-isotopy and produces a smooth function from M cross I to I with no critical points. I'll tell you what this map is in a bit, but it exists. And it gives me the structure of a fibration where the fiber is the isotopic group, I of M. And I'm going to tell you what that is in a second, but basically, when I am in this situation, this is a very favorable situation to be, because if I have something like that, then I can get information about the homotopic groups of the space in the middle by having information about the homotopic groups in the base space and the fiber. So if I know how to calculate homotopic groups of epsilon of M, I will have good control over homotopic groups of the pseudo-isotopic group of M. That's the big picture. Okay. That might be a little bit too much to offload. So how do you feel about the big picture? I'll try to make it a little bit more precise along the way, but this is the strategy. So
let me say that this was Cerf's big idea, right? Because so we're trying to study pseudo-isotopies, which is of M. So we're trying to understand diffeomorphisms of M. And nowhere in that do I mention having to study Morse theory or families of smooth functions or anything. I'm trying to study diffeomorphisms of M. It doesn't seem to have anything to do with studying smooth functions on M, or like at least, you know, Morse theory. And here we've linked that problem of the pseudo-isotopic problem to Morse theory, right? Because now because the thing on the bottom, E of M, that's families of functions on M with no critical points. So that's a Morse theoretic thing. So this was the first step, and that was the crucial idea of Cerf. We're studying the pseudo-isotopic problem using Morse theory.
Yeah. So basically, like at the very least, for what I'm about to do next, what I want you to feel motivated about is that it's a good idea to try and write down a map from P of M to epsilon of M. So that's what we'll try to do. So you're gonna give me a pseudo-isotopy, and I will produce a smooth function from it. That's what I'm gonna do. Okay. So and then we're gonna see how that will be useful. But I seem concerned about something.
Yes, that's what I was doing.
Yeah.
Just remind me, sorry, epsilon of M is functions on M cross I, did you say?
Yes, it's functions of M cross I to I, and they're smooth and okay, precise. So okay, so first thing to note is that the space of pseudo-isotopies acts on the space of real valued functions on M cross I. How does it act there? There is really only one thing you can do. So you have, I guess, you have, if you give me a function from M cross I to I, and you also give me, so maybe this is F, and you also give me a diffeomorphism sorry, and you also give me a diffeomorphism from M cross I to M cross I, that's my pseudo-isotopy. There isn't much I can do to produce, sorry. For some reason, my Apple Pencil decided to stop working. Hopefully it's just the battery issue, so hopefully it's gonna be back soon. But let's see. Yeah, there's only one way that I can go on about a function from M cross I to I. So I'll have to precompose by a diffeomorphism of M cross I, which is the one that I have. And in order to get, I mean, when I'm precomposing by diffeomorphisms, I always have to do it with the inverse. Otherwise, I'm not going to get a group action. But that's really the only thing I can write down. And so I have this action. That's good. We're making progress. We have an action of the pseudo-isotopic group now on this group of smooth functions. We also know that this action stabilizes the subspace of smooth functions with no critical points. That's because we're just precomposing by a diffeomorphism. So if you didn't have any critical points to begin with, you are not going to have any critical points after precomposing with a diffeomorphism. So in particular, what this implies is that I actually have a restricted or like an induced action of the pseudo-isotopic group to the group of smooth real-valued functions on M cross I with no critical points. Okay, so we have a left action. Oops, sorry, that's what I already had, like this. Okay, is everyone relatively happy about this? Okay. Now I want to use that to get a map from the pseudo-isotopic group to this space epsilon of m. Well, I'm in a good spot because I have an action of the pseudo-isotopic group on this space, and I also have a distinguished element in that space that I like, which is the projection to the I factor. So those two things will give me the map.
You're just gonna act on pi2.
Precisely. So if you give me a diffeomorphism, so a pseudo-isotopy, so a diffeomorphism from M cross I to M cross I, I am going to produce a map which is acting on pi2. So it's pi2 composed with the inverse, and that will go from M cross I to I. I guess there is a schematic of that in this diagram as well. So that's yeah, that's the actually I think I wrote this diagram wrong. Right, I think that's what I wanted to write. Okay, so are we okay about how this map is defined? And what are some things that we know about this map? Yeah, so what is the pro image of pi2 under this map? That's the question. That's one first question that we can ask. Right, so if so basically, if I have that pi2 composed with the inverse equals pi2, that means that the inverse is level-wise preserving. And in particular, D would be level-wise preserving. So it must be an isotopy. So if I look at the pro image of the projection, so here if this pi2 composed with the inverse is just pi2, if I look at the projection to the I factor, its pro image is just going to be the group of isotopies. That's like what I promised you up here. Okay, so we have and this space has a base point, and the pro image over the base point is what I wrote down here to be. Okay. How are people feeling? Yeah. Okay. Now we're slowly getting into a bit of a technical territory, but the thing that I want is, I said that I want to somehow use the homotopy groups of these guys to gain information about the homotopy group of the pseudo-isotopy group. I can't do that if P is like any old map. I can do that in some favorable situations. So if P happened to be a fiber bundle, I would have a long exact sequence of homotopy groups associated to it, and I could gain such information. It turns out there is like a weaker notion, which is this notion of a fibration. And it's being satisfied by this map P. So this is, well, either a recall or an acceptance, but if I have a map P from a total space to a base space, this is called a fibration if it satisfies the homotopy lifting property. So what's the homotopy lifting property? It says that if I have a homotopy on the base and the Apple Pencil works. Let's see. So if I have a homotopy for like any map, basically, from any topological space, have a homotopy on the base, and I have a lift of that homotopy at level 0. So this is data that I have. Then there exists a lift of the entire homotopy on the total space. So that's what this homotopy lifting property is, and then there's the definition that a fibration is a map that satisfies the homotopy lifting property with respect to any topological space X. So this is what the homotopy lifting property of this map with respect to X says, and then there's the definition that if this map actually satisfies this property for any X, then it's a fibration. And there are, you can also make some weaker notions. So you can ask for P to satisfy this property, not for any topological space, but just for CW complexes. And there you get into a notion of the Serif fibration, which is also quite as good for our purposes, but we can be quite general. And the thing that we need is basically, yeah, if you are in this situation where you have a fibration, it's a very favorable situation to be, and you can get information about the homotopy groups of the total space using information about the homotopy groups of the base and the fiber. I should say that for a fibration, you have that all fibers are going to be homotopy equivalent to each other over each connected component. So you can like talk about like a fiber if you so please. And maybe, well, here is one very strong way, one very strong criterion for showing that a certain map is a fibration. It's like if it admits a section, right? So if I can write down a map S from B to E such that S composed with P is the identity, well, then I can lift everything. Like I can lift the world. Like I just compose with this map and I can lift whatever you give me. Okay. So the homotopy lifting property is like is a weaker notion than having a section, but if you have a section, that's just what we're going to do. So we're gonna construct a section from the space of maps from n cross I to I with no critical points, to the pseudo-isotopic group, right? So this is a little bit of a more difficult map to construct. So I want to pause and ask for questions or concerns. I'm happy to go over. This is a little bit, it's a little bit rough if you haven't seen this before. So we can, yeah, very strong. Okay. Yeah, okay. You don't need to know, I mean, this is just as like why we go through the trouble of trying to construct a map the other way. But it's quite interesting to try and construct the map the other way anyway. So even if you don't believe in this, like it still would be interesting to try and see what the construction looks like. But so this construction would require some extra data that that we can take from the beginning. So we need the data of a Riemannian metric on M. And then if you give me a Riemannian metric on M, I can find a Riemannian metric on M cross I by taking the product metric with the Euclidean metric on I. So now what's happening is that if you give me any function on M cross I, so it's like any function from M cross I to I can, using this Riemannian metric, I can consider the gradient vector field. Okay, this is the gradient vector field of F with respect to that Riemannian metric. And so there's the following map that I can write down, which is the map from M cross I to M. I'm going to tell you what that map is, but I also want to give a picture of what it does. So again, if you take our favorite picture, like M to be the circle, M cross I is the cylinder, what the data that I have gives me is that I have this gradient vector field. In particular, I have gradient flow lines that I can draw.
And it's nowhere vanishing, of course.
Because exactly, that's where we're using that F has no critical points, precisely, yeah. So, yeah. So for example, this could be a flow line that I just have like on the left, okay? So, so I'll be using these flow lines to define this map from M cross I to M. And so what I will be doing is, if you give me any point on M cross I, I'm going to ask myself, okay, which flow line passes through this point? So if you give me, say, this point here, well, this orange flow line that I gave you passes through this point. And then look at where this flow line takes this point in the base. So it's like here, it will take it to this orange point, which is just this orange point. That's the image of the map. So the map alpha of F takes this point W and maps it to the initial point in M cross 0 under the flow line that passes through W. That's what this map does. Is that fairly clear? Mm-hmm. Now, this is just the map from M cross I to M. I promised you a map from M cross I to M cross I, because I promised you a pseudo-isotopy, right? So, but that's, well, I mean, everything is okay if I say it's okay, but there is a fairly like reasonable thing that you can write down as a map from M cross I to M cross I, which is in the M direction, use the map alpha F that I just defined for you. And then in the I direction, I just need to tell you what height to prescribe to point W. But there is a reasonable notion of a height that I can prescribe, just F of W. Sorry. Okay. That's my map. So that's a map, beta sub f. It takes as input a function f from n cross I to I. That's the input. I have fixed the Riemannian metric on m, so that's not that's in the background. The input is a smooth function from m cross I to I. The output is a map beta f from m cross I to m cross I, which I'm claiming is a pseudo-isotopy. Okay. Now, life's not that easy. So this is actually not how S is defined exactly. So S, my section, takes as input this function with no critical points, but the output is not going to be exactly beta of f, it's going to be the inverse. I'll justify that in a second, but that's how S is defined. Before I justify that, I want to pose and ask for questions regarding how S is defined. So it's like, right, I'm taking a smooth real valued function. I have, with no critical points, I have a Riemannian metric that gives me flow lines all around my manifold. And I can use those flow lines and the function to construct a map from m cross I to m cross I. And that's my pseudo-isotopy. I'm just using the inverse of it for a reason that I'm just going to tell you, but that's the idea of the construction. Because if you wanna write down maps like this from m cross I to m cross I, you need to tell me what to do in the m direction. You need to tell me what to do for the I direction, and the m direction is governed by the gradient flow lines. The I direction is governed by the function. So, so I just want to justify to you that so running a little bit over time, are we? No, it's fine. I just want to justify to you that this map S is actually a section. So I want to justify that P composed with S is the identity. What is the construction of beta sub f tell us? Beta sub f is the pseudo-isotopy from m cross I to m cross I. And if I start here and then project by pi 2, the value that I'm getting is f of w, right? That's how I defined beta sub f. That's the height that I am prescribing to it. So now if you just that's the definition of beta sub f. If you just trace this diagram back, what you have is that P composed with S of f. Well, S of f by definition is beta sub f inverse. And this, by definition of P, is pi 2 composed with beta sub f inverse inverse, which is just pi 2 composed with beta sub f, and that's just f. So that was just the reason for this extra minus sign. Still annoying, but that's the yeah. So the P, so this function that we constructed. So where am I? So I constructed two things for you. I constructed a function that goes from the pseudo-isotopy space to the space of smooth real-valued functions with no critical points on M cross I. And I also constructed a function going the other way around, S. And I justified that pi composed with S is the identity. That's what we did. And now for basically formal reasons, that implies that in the connected component of pi2 in epsilon of M, all the fibers are homotope equivalent to the isotopic group of M. But I'm not even going to use that because we can actually prove directly that, let me write down again what the map is. The map is P of M to epsilon of M, sending D to pi2 composed with the inverse. And the claim is that if you give me any two pseudo-isotopies, D1 and D2, they are going to be in the same fiber of this map, if and only if there is an isotopy such that D1 composed with this isotopy is D2. Again, I'm using isotopy and diffeomorphism used by isotopy interchangeably, but so that's what I want to prove now. I just want to is the claim clear? Is what I'm trying to prove now clear? Yeah. Okay. Because then the proof is basically if D1 and D2 are on the same fiber, that by definition means that pi2 composed with D1 inverse is pi2 composed with D2 inverse, which is the same thing as pi2 composed with the composition of D1 inverse with D2 equals pi2. And that's exactly so this here is the level-wise preserving requirement. So that just implies that D1 inverse composed with D2 is level-wise preserving, and so it's an isotopy. And I can take this isotopy here. If I compose with D1, I'm just getting D2. That's how this proof works.
Why is D2 composed with D1 why is it level preserving?
So that's so the assumption that I'm making is that D1 and D2 are on the same fiber under the map P. And P is the map that sends, so P sends D1 to pi2 composed with D1 inverse, because that's what this map is. It sends D2 to pi2 composed with D2 inverse. And so being on the same fiber means that those two things must be the same. And those two things being the same means that this a priori pseudo-isotopy, so D1 inverse composed with D2, I can either project to the I factor, or I can apply this and then project to the I factor, and I get the same thing back, which is of being levelized preserving. The I factor is my levels. I don't know if I made this more confusing than that it needs to be. Yeah, so I just want to give you basically the main proposition. I'm not going to prove it now because I think it's better to end here. But the main proposition that sort of like makes everything work is this one, which is if you give me a pseudo-isotopy, okay, then what I have is I have two smooth functions that I can write down from n cross I to I. It's the smooth function that we all know and like, which is this pi2, just the projection to I. And it's another smooth function with no critical points, which is this pi2 composed with the inverse. I have these two smooth functions. And now there is the question of, does there exist a path of smooth functions without critical points that goes from one to the other? And that question is entirely equivalent to, is the pseudo-isotopy D isotopic to an isotopic? Right, so a priori, I know that, I mean, this space epsilon of m, it lives inside this huge space of all smooth functions, potentially with critical points. So I know that like any two smooth functions I can connect with the path of smooth functions, but I don't a priori know whether I can do that in a way that all smooth functions in the path have no critical points. If I can do that, then the pseudo-isotope that I began with is isotopic to an isotopic. That's what this proposition says. And it's not difficult to prove, but I think it might be wise to end with the statement of it and pick up next time, because I'm always a bit conscious of leaving the hardest part towards the end of a 2-hour thing, which is exhausting. So I think that might be a good stopping point for this week.
Thanks, Filippos.
Are there any
questions? Yeah.
The second half was a bit more technical than the first half, but
if you go back to that diagram here of the vibration,
yeah.
This is maybe a bit of a random question.
Do you mean this?
Or no?
Okay.
Just
The lifting property
yeah,
of
the
vibration.
Yeah.
Like that diagram, is there something categorical? Like,
yeah, definitely.
That looks like the dual of a strong epi diagram.
I don't know enough.
To me, at least. I was just curious.
The dual of what?
The strong, like the strong epi. The strong epi more endless.
With the inclusion on the left.
Well, if you invert all the arrows, then I think you get a strong epi property. And I was just wondering if there's something going on there. But it's very random.
Yeah, I'm not sure. Well, I'm not, but first of all, I don't know if the strong epi property is, so I'm definitely not sure. But
what is the strong epi property?
yeah, that's
so an arrow is a strong epi.
Okay.
Yeah.
It's the same. No, all the arrows are the right direction except the diagonal. The diagonal should go the other direction, but all the others need to stay as they are. Maybe. Oh no, wait. If we reverse it, no, never mind. That's okay. It goes like this. Yeah. So P is the strong epi. If for any diagram like this where this is a mono, so essentially an isomorphism, then there exists a unique map here which makes everything commute. And this is sort of
Unique, it was just existence.
it's unique. I think it's unique, yeah.
Unique.
oh, then it's definitely not.
But
Because
okay, so
the whole population property, I don't think
this is sort of the same, but now we just swap all the arrows. So. Oh.
Just draw it in the same, rotate your diagonal
Yeah.
90 so it's the same piece.
So that would be. Maybe I have to do this swapping arrows is going on here. What's the erase?
It's easy.
Oh, we're using so we have
Well, now you rotated it the wrong way. Like but our map must we wanted to go down. Like his map went from E to B. Like it went downwards.
yeah, but the
Bruce says you want
You want
A here and
yeah.
B here.
Yeah.
okay, so you okay.
Wait, what?
So
You didn't rotate. What did you?
I
happened?
reflected,
You
yeah.
reflected. Yeah, D.
Okay, so you want the thing is the arrows will go the wrong way now. Because there's this dual in the he goes there.
There.
So that's just me. I think I'm going to stop the Zoom and everything now.
Okay.
I
Shall
mean,
we ask if
maybe there's
people
more
here
relevant
have questions? Is anyone left here or
I asked and
no questions? Perfect.
not.
Yeah.
Thanks for the talk. Shimwell says thanks. So we'll just email the slides and that's fine. So, but we can stop that now. I think it's better.
Yeah,
Yeah, we
that's
can-
good. Yeah.